We have another rule about derivatives that we're going to be talking about, and it's called the chain rule. The chain rule is a rule that happens or is used when it's a composition of functions. And it's kind of like this: f of g of x, it's where there's a function g of x that's inside of f of x, or it's in the x place of f of x. I'll show you some examples in a minute, but the formula is that the derivative of a composition is the derivative of f of x with g of x inside of the derivative times the derivative of g of x. So basically, you find the derivative of inside, and then you multiply by the derivative of f of x, where g of x is still in the place of x. And I know that sounds really strange, but we're going to look at some problems, and I think it'll make sense once we look at some problems. So here's some examples out of your book, and just kind of to get you in the idea of why we need the chain rule. These are problems without the chain rule. You don't have to use the chain rule to find the derivative because they just automatically use the power rule. Like this derivative here would be 2x. This derivative here would be cosine of x. This derivative would be 3. These are just normal, basic kind of problems. The derivative here, the derivative of x is 1, and the derivative of tangent is secant squared, or 1 over cosine squared. But if we look over here on the right-hand side with the chain rule, these are problems where you can't just do the power rule. And it's because there's a function inside the other. For example, on the first one, y equals square root of x squared plus 1. X squared plus 1 is inside the square root. So you have to use the chain rule. On the next one, y equals sine of 6x. 6x is inside of the function of sine. So you have to use the chain rule. On the next one, y equals 3x plus 2 to the 5th. 3x plus 2 is inside the function of something to a power. In the last one, x squared is inside of tangent. So it's when there's a function inside of a function, and that's what we're going to look at. So first of all, I'm going to do those problems that we just talked about that need the chain rule, and then I've got a few more other examples that we'll talk about. So here, this x squared plus 1 is inside the given function. So what you do, the way you start off, well, first of all, before we start it, I'm going to rewrite this as x squared plus 1 to the 1/2, just because that is easier for me to look at. It's raised to a power. The yellow is the inside part. So what you do is you do the derivative using the power rule. 1/2 is a power, so you use the power rule. The 1/2 comes down in front of the function. Leave what's in there alone. Subtract 1 in the power. So 1/2 minus 1. So you get that. So that's the first part of the chain rule. The second part of the chain rule says that you multiply by the part that's the derivative of the part that's inside. So I want to multiply by the derivative of that yellow part that's circled. Well, the derivative of that part is 2x, so I want to multiply by 2x. So you do the power rule and you leave x squared plus 1, and then you take the derivative of what was inside. Alright, the only other thing that needs to be done to simplify here is that you can multiply this 2 and this 1/2 to make 1. And then you have x. I'm going to put the x in front, and then you have x squared plus 1 to the negative 1/2. That's just a simpler, simplified way. Okay, on the next one, sine of 6x. What the 6x is like the inside function again. So to use the chain rule, you find the derivative of sine of something. Well, the derivative of sine of x is cosine of x. So it's cosine, and then you leave 6x alone. Then you multiply by the derivative of 6x, which is just 6. That's the chain, that's the part that's extra. And you can leave it like that, or you can put the 6 in front of the cosine of 6x if you want to. Alright, on this one, 3x plus 2 is inside of something to a power. So to start this one, I find the derivative using the power rule. 5, leave 3x plus 2 in there, raise it to the 4th. Then I go back and multiply by the inside part, which is the part in parentheses. That is 3. And so we have that. Only way to simplify that is to multiply the 5 and the 3, so I get 15. 3x plus 2 to the 4th. Okay, on this one, we have x plus tangent of x squared. Keep in mind on this one, the way that they have that squared above the x, that just means that only the x is squared. So it's tangent of x squared. If they want that tangent to be squared, the parentheses does change, and I'll show you one of those in just a minute. But that one is just meaning x squared. So we find the derivative of x, which is 1, and then we find the derivative of tangent of something. And we did that proof in the example with quotient rule, if you change that to sine and cosine and solve it. So now we just are going to use that rule. The derivative of tangent is secant squared of x, or 1 over cosine squared, whichever way you want to write it. I'll write it like secant because that's what your book does. So it's secant squared of x, but what's in parentheses is x squared, so I put that x squared in there. And then I multiply by the derivative of x squared, which is 2x. Okay, this one looks pretty simple. It doesn't even look like it involves the chain rule, but you can do it with the chain rule. You can do this problem with a quotient rule if you would prefer. Out to the side, I'll do that real quick. Bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. This is 0, so you just get negative 1 over x plus 1 squared. That's if you use a quotient rule, and you can do it that way. Now, if you want to use the chain rule, what you would do first is you would rewrite this as x plus 1 in parentheses to the negative 1 power. If it was a different power on the bottom, then I would probably bring it up like I did and raise it to a power. The only time that you want to bring it up like this is if you have a number on top. If you have something with an x on top, you're going to want to use the quotient rule. If you rewrite it like this when there's an x, you're going to have to use the product rule, and it gets really complicated. So the only time that you can do what I'm doing here is when there's a number on top. So if I'm going to do the derivative using the chain rule, I'm going to use this, and I'm going to use the power rule first. Negative 1 times x plus 1, subtract 1 in the power to the negative 2 times the derivative of the inside, which is 1. And so this is our answer, and notice that both of these answers are the same, they're just written a different way. Alright, as I told you before, I was going to show you another example where the squared was at a different place. This is the same as sine of x in parentheses all squared. And I usually, if I'm going to find the derivative of something that has a squared like that, you do have to rewrite it. I think it's easier. That's up to you though. If I'm going to do the derivative though, I'm going to do the power rule to 2. 2 sine of x, subtract 1 in the power, so it's just to the first. And then I multiply by the derivative of the inside, which is cosine of x. I'm going to throw in one more example here. And let's say it was y equals cosine squared of 3x. If I were going to do that problem, I would rewrite it as cosine of 3x all squared. So if I do the derivative, I bring down the 2 with the power rule, leave the cosine 3x there, subtract 1 so it's to the first, but then I multiply by the derivative of the inside. Well, the derivative of sine of something is negative sine of the thing. Again, leave 3x in there. This is a time where you have to use the chain rule one more time because there's still an inside, and the derivative of 3x is 3. So it's like there's several chains in this problem if you want to think of it that way, and the fact that you have to find the derivative of cosine of 3x, and then you have to find the derivative of the 3. If I were going to finish this, I could multiply the 2 and the negative 1 and the 3 all together, and then I would just put cosine of 3x and sine of 3x behind it. Alright, this one is similar to some of the others. What I would do first is I would just rewrite that to the 2/3 power because we have a 2 here and a 3. The number on top is the power it's being raised to. The number on the bottom is the root that's being done. So to find the derivative there, I would put 2/3 in front. Subtract 1 in the power, so 2/3 minus 1, which is negative 1/3. And then multiply by the derivative of the inside, which is 2x. The only other thing I could do is multiply the 2 and the 2/3 together and get 4/3. Alright, this is another one that you could maybe use the quotient rule for, but it is a little bit more complicated, so I would probably rewrite it with a -7 and then bring that to the -2 power. Remember, I have a number on the top, so it is okay to do the chain rule this way. And then here, I'm going to multiply -2 times 7. Leave the 2t minus 3, subtract 1 in the power, so I did the power rule, and then I multiply by the derivative of the inside, which is 2. The only other thing to do is multiply the 2 and the -14 to get -28, and then we're done. Alright, number 9. This is the same as cosine of x cosine of x to the 1/2. The cosine is not to the 1/2 power, it's only of the square root of x. So rewriting that and understanding what it means is really important. So here I do the derivative of cosine of something, which is negative sine, and you leave the x to the 1/2. But then I multiply by the derivative of x to the 1/2, which is 1/2 x to the -1/2. You can multiply the 1/2 and the negative together, so I would get -1/2 sine of x to the 1/2 times x to the -1/2. Okay, on number 10, this one is the opposite of what we just saw. The cosine is being raised to the 1/2 power, so it's written that way. So the derivative, I use the power rule, and I get 1/2 cosine of x, raise it to the -1/2, and then the derivative of the inside, which would be negative sine of x. So when I multiply there, I get -1/2 cosine of x to the -1/2 times sine of x, and then that's it. Alright, the interesting thing about the chain rule is that you can use the product rule and the quotient rule along with the chain rule. There are problems where all of those are involved. We'll be looking at those, but you can think ahead that there are times where you have to do all those kinds of things and look using all the rules in the same problem. It does get long and a little complicated, but that could happen. There's your 3 try problems. Always remember to think about what's inside and leave it, and then find the derivative of it at the very end.